All right, and the miscellaneous here is just the reason it's called x86 is because the chips were called the 8086 and then 8186, 286, 386. Had to get that out of the way. You know, for Mac people like me, you know, I don't know why it's called x86. I've been using, you know, Motorola chips and IBM chips and PowerPC things all my life. So just getting that out of the way. All right. So here's what you're going to learn in this class. We're going to take things like simple C programs, and we're going to say, you know, the background prerequisite for the class is that you must be able to understand a program like this, right? So there's nothing scary or new about the whatever you'd say, number sign, or what's the other name for it? Hash, yeah. So nothing strange about the syntax, hopefully. So this hello world, and specifically one where we're returning hex 1234 at the end, okay, that's the same as this sort of assembly. And you don't need to necessarily understand what it means right now, but you know, you can see in this there's some hello world, and you can see a printf, and you can see a hex 1234. And then so our goal here is to figure out what all that stuff surrounding that is, right? What's the point of the rest of it? And so this was, if I compile that hello world in Visual Studio Express C++ 2005 with buffer overflow protection turned off, etc., to make it simpler, this is the assembly you generate. But that's the same thing as this, and so if I do it on Ubuntu with GCC 4.24, instead I get this. And again, we have only one call here, but it's a call to putS, and so okay, maybe that's an equivalent of printf. And let's see, there's hex 1234, and I don't see hello world, so there's a bunch of stuff here that needs explaining, basically, right? And that's also the same thing as this, which was compiled on Mac OS X 10.5, so that, like I said, 10.6 and greater is 64-bit code. So on 10.5, using GCC 4.01, you get this code. And so again, looks like we have putS here, hex 1234, and don't know where our hello world string went. But basically, if I turn on optimizations, go back to that Visual Studio one and turn on optimizations, this is what it can boil down to. So there's a push of the string hello world. Essentially, it's not actually the string. You push a pointer to the string. There's a push of a string, there's the printf, there's a pop, we don't know what the point of that is, but then there's a 1, 2, 3, 4, and there's a return. So this is, you know, this is the optimized code. It's much fewer assembly instructions, and they do seem to like pretty well map to the C code. You got your string hello world, you got a printf, and you got a 1, 2, 3, 4, and a return. Right. So the good news is, and this is why, you know, I think a class like this can be fairly effective of getting you bootstrapped onto x86. Good news is that by at least some people's measure of code complexity, only 14 assembly instructions account for 90% of code. So this was a Black Hat talk where the guy was trying to generate a discriminator to say this is malware, this is not malware, based on like x86 assembly frequencies and stuff like that. And so amongst that, he could say, well, the frequencies say that it looks like these 14, you know, he just would bin them and say, okay, 14 instructions make up the top 90% of code. So for all these assembly instructions, take 14 of them, and that's 90% of it. And so I generally find that about 20 to 30 instructions 20 to 30 instructions is pretty much good enough as far as I'm concerned to make it so that you don't have to keep going back and forth to the reference manual. So once you go through this class, then ideally you won't have to go back and forth. You'll still have to look up some special stuff as it comes up, but we go into looking stuff up as well. And actually, if you go back and you count all the instructions in those Hello World variants that we saw, that's actually 11 things thus far, and actually, you know, most of them are due to the complex Ubuntu one, right? So there's a lot of different instructions here: LEA and push, move, etc. So now we're going to do a couple of refreshers quick so that we're all on the same page here. So this picture is taken from the Intel manual. They're fundamental data types. What Intel calls a byte, you may, call a char in C. Not a car. For people who say car, they're messed up. It's a char. A byte is a char. A word in Intel's notion is what you may put as a short. And note, it's called a word because this was set up back when they were 16-bit things, right? So the original 8086 were 16-bit processors, not 32-bit. So to them, a word of data was 16 bits. And so that's why then a 32-bit value is called a double word. So when they moved from 16-bit to 32-bit, well, this is twice as much as we were used to dealing with before, so it's double it. It's a double word. And you got quad word, etc. And also, it's good to know. So you may have things like this. And you may, if you're used to like ANSI C or writing stuff in POSIX, etc. You may be used to just using these straight up C types: char, short, long, or int, etc. And if you're used to Windows programming, Windows will like type def something like a long into a double word, and they call it like a D word. So in Windows programming, you may see D word, Q word, things like that. That goes back to this Intel notion of it's a double word, it's quad word, etc. All right, so alternative radices. This is something you definitely want to memorize. Basically, if you do any sort of dealing in assembly, you're going to be able to need to know. Really, it's more the hex and binary translation. You're going to want to know how to go back and forth with those, but still for your own purposes, you may still want to know how to go back to decimal. But the nice thing about this is, if you look here, you'll see that this entire 0 to 15 over here in the binary side, everything up to 15, is represented in hex, and so 4 bits is called a nibble, right? So 8 bits is a byte, 4 bits is called a nibble, and a single hexadecimal character is essentially a nibble, right? So you can have hex F, that's 4 bits, and that hex F is always going to translate to 1111 in binary. And so when you memorize these translations between hex nibbles and binary nibbles, you can essentially go back and forth pretty quick, and that can become necessary when you're doing like bitwise operations and things where you're XORing two strings of bits together. You need to go down the line and do each of those bits one at a time. Use the XOR operation, use the AND operation, use the OR operation, one at a time. So if you see something like, okay, Bill, I'm going to go over to the board here for a second. All right, so you'll frequently see 32-bit values. Let's see, 2, 4, 6, 8. 32-bit values represented as a string of hex nibbles, right? If I take each of these in turn, and I can, if I know what their translations are into binary, it can be useful for doing the math yourself in terms of if you're doing some OR operation. So let me just do that again. So let's say I was doing like this, and frequently what you'll see for like bit masking or something like that is you'll see like F, maybe 0, F, 3, 0, F, or something like that. And so if you need to do this sort of thing, what you do is you just deal with it one nibble at a time first. And so you say, well, 2 in binary is 0, 0, 1, 0, and F in binary is 1, 1, 1, 1, and then you just go down the line and you do your AND. So 0 and 1 is 0, 1 and 1 is 1, 0 is like that, and then you turn that back into hex, and so you say, well, this is hex 2, so that's 2. And so in some sequence, in lots of cases, you may want to do this mentally. In other cases, you'll just say, okay, well, I'll step through with the debugger and I'll let the debugger do it, and I'll see what happened afterwards, and I'll figure out what's going on due to that. But this is why knowing your conversion between radices is very important, so that you can do this quickly if necessary, so that if you just see something where it's like subtracting C, you can know, okay, it's subtracting 12, something like that. All right, so in your slides here, you'll probably have a thing after this, but I'm just going to get into negative numbers to this degree, and we're not going to go into the digression in terms of why negative numbers are represented this way. But negative numbers, if you didn't already know, they're the 2's complement of the positive number. A 2's complement is defined as a 1 complement plus 1, and a 1's complement is defined as just flip all the bits. Right? So if, I'm going to go back over to the, well, never mind, sorry. I'm just going to use these examples. I don't need to rewrite them. All right. So I said 1's complement, flip all the bits, and then 2's complement, 1's complement plus 1. So let's say I have the number 1 right here, right? So 0, 0, 0, 0, 0, 1 in binary or in hex. And if I 1's complement it, then I flip everything so it's 1, 1, 1, 1, 1, 0, right? And so in hex, if I again, so you can see I can take these 4 bits and I can turn those back into E, and I can take these top 4 bits and I can turn those into F because they're all 1s. That's F. All 1s except for the last one is E. So that's the 1's complement value, and then if I add 1 to that, then I get 1, 1, 1, 1, 1, 1, and that's FF, and that's how you represent negative 1. So this is like a 1 byte sort of number here. So this is 8 bits. It's going to be 1 byte. So a 1 byte positive number is 1, and the negative number is FF. And so basically between 1 and 7F, those are all your positive numbers that can be represented through 1 byte. And from 80 to FF, those are all the negative ones. And so FF is negative 1, and then FE is negative 2. And so you just kind of count backwards from FF in order to get your negative numbers. And the exact same thing holds for when you have, 32 bits worth of things. You just, if FF, etc., that's all negative 1, then you just subtract 1 to get negative 2, right? So that's why it sort of makes sense, right? Negative 1 minus 1 is negative 2. And so I just show the simple example here. If this is 4, so we've got 4 right there, 0 in the 2s, 0 in the 1s. 4 is represented in binary that way, and so if I just flip all the bits, this is going to be the 1's complement of 4, and then I take that plus 1, right? So 1 plus 1, that's going to, carry the 1, so that's going to be 0, carry the 1, and then now I have 1 plus 1 again. It's going to be 0, carry the 1, and so I get 1, 1, 1, 1, 1, 1, 0, 0, and that's what we see over here, right? 1, 1, 1, 1, 1, 1, 1, 0, 0. All right, so this FC is therefore negative 4, and so if you start at FF, which is negative 1, you count backwards. FE is negative 2, FD is negative 3, and FC is negative 4. And again, this is why you want to know your conversions back and forth between the things, right? You need to be able to count backwards, forwards, change the radices any direction, jump over to decimal, -5, go back over to hex, etc. So counting backwards and forwards and all that is, if you spend any amount of time dealing with it, you'll pick it up, but it's the kind of thing you need to know right now that you're going to have to know later if you're going to want to deal with it frequently. Or you can just always have the calculator open. That works too. All right. So a little bit about architectures, because the architecture was in the title, so I have to talk about it a little bit. Intel is a CISC, or complex instruction set computer architecture. And so in CISC architectures, what you do is you just keep layering on more and more instructions. You got some new thing that you find that lots of people are doing frequently, like the compiler always needs to generate this sort of sequence of instructions. Okay, let's make a new single instruction that does all of that in one instruction. So with CISC, you just keep adding more things in. In particular, on Intel, we have variable length instructions. So that means you can have 1 byte instructions, or they can theoretically be up to 16. I'm not sure what the actual longest maximum valid one is. I think it's more like 15, but by some naive computation that I made based on the way it says at the beginning how to put instructions together, theoretically 16 can be the biggest, but I think it's a little bit smaller than that. So instructions will vary between 1 and say 16 bytes. And for anyone out on the internet who's watching this, if and when this becomes public release, please feel free to tell me what the maximum instruction is. There we go. I'm just going to keep making plugs out to the people on the internet to correct me. I'm sure they'll correct me with gusto. All right. So the other major architecture is called RISC, or Reduced Instruction Set Computer, and as you might guess from the name, it's sort of a pushback against the stuff that was going on with CISC, where they were just keep adding things. And so this came out of some academic work where they said, hey, most of the time we're only doing, this small subset of your RISC thing. The compiler writers don't know how to use all these things. They can't figure out the best way to generate code from high-level code, which uses all of these instructions that you put into your architecture. So we're going to go ahead and try to figure out what this reduced set of instructions is, that we can still get pretty much everything done, and maybe we'll need to use a couple more instructions, but we'll still be able to get everything done. So most all of the other major architectures actually are RISC, so PowerPC, ARM, Spark, MIPS, etc. And these also typically have more registers, so whereas Intel has only very few registers that you can use, RISC machines have like a ton of registers. Because they've got less instructions, they need to be holding things in registers and juggling more data, stuff like that. And frequently they're fixed size instructions. So whereas I said Intel can be between 1 and 16 bytes, RISC architectures, typically they're fixed at the size of whatever the data size is for that CPU. So if it's 32-bit architecture, the instructions are 32 bits, 64 bits, the instructions are 64 bits. All right. So a little bit about endianness. So this comes from Jonathan Swift's Gulliver's Travels, and it has to do with pointless wars between England and France. So it was an allegory on England and France, and they're going to war over nothing particularly meaningful. And in Gulliver's Travels, Gulliver came upon people who were having wars over whether you should break your hard-boiled egg at the big end or the little end, right? So take your hard-boiled egg, flip it one way or the other, and crack it open and eat it. And so what it basically means is it doesn't really matter. There's no functional difference, right? But endianness, same thing with computer architectures. There's no functional difference which way you do things. But if you have a little endian architecture, what that means is you store the little end, or the least significant byte, first in memory. So if you have low addresses in memory, so let's say your addresses start at 0, if you're doing little endian for this number 1, 2, 3, 4, 5, 6, 7, 8, you would take 7, 8, that's 1 byte, and you'd put that at address 0, and then you'd put 5, 6, and then you'd put 3, 4, and then you'd put 1, 2, right? So that means your little endian goes at the low addresses in memory. And with big endian, it's the exact opposite. You just start with, address 0 would have 1, 2, then 3, 4, etc. And so Intel is little endian, so you have to keep that in mind. Things are stored big endian in registers. So when you're looking at a value in registers, the value 1, 2, 3, 4, 5, 6, 7, 8 is 1, 2, 3, 4, 5, 6, 7, 8 in the register. But if you go back out and you look at it in RAM, and if RAM is currently displaying it in the sequence of sequential bytes, it'll look like 7, 8, 5, 6, 3, 4, 1, 2, and you'll have to mentally flip that back around. So be aware of that. When you're looking at RAM, stuff will be stored little endian on Intel. When you're looking at it in the registers, it's just a normal value, like you, the human, would be, well, you, the English-speaking human, who uses the most significant bits and bytes at the left-hand side. That's what you're used to, right? And so those other architectures that I was talking about besides Intel, they tend to be either big endian or bi-endian, meaning they can go either way. So like PowerPC, you can technically flip it back and forth between big endian or little endian, but by default they typically are always big endian. So here's a simple little picture of describing what I was just saying, right? So if we pretend this is our RAM, and we say that RAM has a sequence of byte-sized cells stored in it, then on Intel you may have hex feed face, and this will be stored with this little end first, right? So this is the least significant byte. That goes into the lowest thing. The little end goes in first, and then etc. And big endian, it's the exact opposite, right? So the big end goes at the low address. So that's kind of a good way to visualize it. If you get confused, everything is always in the registers, hex feed face, but in memory, if you're trying to like read memory out on big endian, it would make sense. You'd look at memory and it would be, you know, maybe from left to right, you know, displayed horizontally, and you'd be like, oh, feed face, okay. But on Intel, you have to think, okay, stuff is going to be backwards. And another thing, just to clarify, endianness has nothing to do with at the byte level, right? So sometimes people get confused of like, maybe my least significant bits are flipped around as well, like so I have a single byte, and like maybe is that the least significant bit that side or that side? It only has to do with the byte level. So CE right here is CE right there. You don't do any bit level flipping around, only byte level. And so this can be equally applicable for, so when I say byte level, that means if you have a short where it's like 2 bytes, 2 bytes can still be flipped around in RAM because it's little endian in RAM. But in registers, it would still be big endian. All right. So digging more into registers, what it is it's a small memory storage area built into the CPU proper, but it's still volatile memory, right? So that means if you power off the CPU, you're still going to lose the state of your registers. And so on Intel, we have 8 general purpose registers plus the instruction pointer, which the instruction pointer is a register which will sort of only be dealing with indirectly when you use call instructions. That's sort of moving the instruction pointer, because the instruction pointer always just points at the next instruction that we want to execute. And so we can't like just move values in there directly, but we can call certain instructions which will manipulate it. So if we say, you know, use a call instruction and go to some subroutine, well, you're implicitly changing these instruction pointer because you're saying, I want you to point at that new code which I want to execute. So got the 8 general purpose where you can store whatever you want in them, and they have different conventions that are used on them, but you know, ostensibly they're general purpose, and the instruction pointer. So 2 of the 8 are very not general, and so then you end up with only like 6 which are kind of general purpose. So again, this class is all about x86 32, so 32-bit things. Your registers are 32-bit long, 4 bytes. And on x86 64, they would be 64 bits. And actually, just to call attention to this right here, down at the bottom of some of these pages, it says book, like page 25 and things like that. It looks like we don't have the books distributed there, and I have a note here saying, I will mail all books to students when the last 3 arrive. So it looks like we were short on books, and so they didn't hand out them here because he didn't want to play favorites or something. But, so I have a book that kind of comes with the class. I'm not teaching to the book, but it was something where I needed something that could give you a different perspective on x86 basically, other than the manuals. So I didn't bring the manuals because they're big and fat and they're like this thick. But I usually like to say, and this is why you're taking this class, so you don't have to read the manuals, there's a littler book which will give you an alternate perspective. So if you want to go back through and see, you know, how the book describes stuff as opposed to how I described it, I kind of call out where in the book you can find different instructions or different architectural things that I go over. All right. Oh, and I forgot to write stuff on the board. Well, do it at break. So Intel has register conventions, which are basically Intel's guidance where they say for compiler makers or anyone who wants to hand code assembly, here's how you should deal with the registers on the system. And what it is, it's sort of like, you can think of it like syntax guidance in C or something like that. You know, people just put out a guidance that says, do it kind of this way so that when someone else comes along and tries to read your code, they understand it. So similarly, you don't have to do it that way. You don't have to use any of these these register conventions, but if the compiler maker uses these conventions, then when someone comes along, they'll be able to understand it. You know, that's useful for even the compiler maker so that they can try to understand if something's going wrong as they're generating code, things like that. So anyways, in this class, I marked these as green. Oh, also I should say, these physical slides you have are out of date. Like, I updated things for the previous class, but they had already printed these, so if necessary, update your things. But green are the ones that we're actually going to see in this class. So the thing is, All of these are conventions, but you need to be aware they're not always being used per convention. So it's more just like if you see something being used a certain way, you can say, aha, it looks like they're using that per convention, but at other times they're just using it as some scratch registers. So, for instance, EAX, which you can't really see very well in that thing, but EAX is green, and it's saying, in this class, we're going to see EAX being used to store the return value from a function. So if I call into a function and the function, returns 0 or returns -1 or something like that. In assembly, what you're going to see at the end is it's going to have some move into this EAX register right before the function returns. That means the register is being used per convention to hold the return value before you exit the function. So that's something we're actually going to see in this class. EBX, on the other hand, I put as a, well, also I should say that I simplified some of this. EAX is also used as the accumulator register, meaning that you'll add stuff into it and build up values in EAX, but I kind of left that off here because we don't really see that in this class. But again, I have the Intel architecture reference right here, so if you want to see what they say that it actually are all the register conventions, you can go look it up, but I simplified these just for our purposes. So we will see EAX used to store return values in this class. EBX pointing to the base of the data section, we're not going to see. I think we may see that more in the Life of Binaries class. I'm not sure yet because I'm still working on the material. But that's I know that's definitely used in GCC generated code, so we may see that a bit. Oh, and also position independent code. That's the big thing. Windows doesn't generate position independent code, meaning that it can go anywhere in RAM. Linux and GCC do have the ability, and I think this EBX is frequently used when you're generating position independent code. It's used per that convention, but we're not going to see it in this class. ECX, on the other hand, can be used as sort of a counter for these certain operations that are going to loop doing the same thing over and over again. And in that case, this ECX is used as a counter, and it's decremented one each time that you go through this operation. So you may do one copy, decrement ECX, one copy, decrement ECX, and then when ECX becomes 0, that means stop copying. So that's one convention which you can see ECX used for, and when it's being used for that, it'll be pretty obvious because there'll be this sort of repeated instruction that we'll probably get to by the very end of today. EDX I/O pointer, you're going to see that in intermediate x86 when we talk about hardware I/O, but not in this class. So, all right, ESI and EDI can be used for source or destination. So ESI, source, EDI, destination, for those sort of repeating instructions or string operations that I was talking about, where something is looping and doing the same thing over and over. It may, for instance, copy from source to destination, decrement ECX, copy from ESI to EDI, decrement ECX. So that's how these may be used per convention. Now, we're definitely going to see ESP being used as the stack pointer. So we'll get into stack a lot, but basically the stack is just a data area. And so as you add data to the stack pointer keeps moving to always point at the top data on the stack. EBP, so that's the base pointer, EB for base pointer. That is when we have stack, each function may get its own new stack frame, which is basically just its own little area that it controls the variables within this area, things like that basically. And so EBP will always, well not always, but EBP by convention can point to the base of the stack frame saying, here's where this function's stack stuff starts, and here's where the stack, the top of the stack is, and so anything between the frame and the top of the stack, that's all owned by whatever function you're in currently. So we'll get into that a lot more. And EIP, as I said, we don't have direct control over this, we have indirect control over this, in that this points to the next instruction that the CPU will actually execute. So you can't just load some address into EIP, but if you call a jump instruction or a call instruction, that implicitly changes this EIP to go to wherever you jumped to or you called to, etc. Any questions at this point thus far about registers or CISC or RISC or the review material or anything like that. Anyone on the phone have any questions, etc.? All right. Okay, so moving on. So beyond conventions for how registers are actually used, there's conventions for how functions agree to not destroy each other's registers, basically. So this has to do with what's called either caller save registers or callee save registers. So caller save registers means I'm a function and I want to call another function. I'm the caller. I'm going to call this other function, but I know that this other function, by this convention, is allowed to modify certain registers as much as they want. So if I call this function, it's, I should assume that it's going to destroy these registers that I'm currently using. The registers are EAX, EDX, and ECX. So if I'm going to call another function, I have to assume that it's going to destroy whatever values I have in EAX, EDX, or ECX. Therefore, I, as the caller, am responsible for, if I have a value in one of these registers that I don't want destroyed, I better save a copy before I actually call the next function. And so basically, for caller save registers, if the compiler generates code where the code currently has something in EAX or EDX, the compiler also needs to generate code that says before you call a function, save a copy of that register off to the stack, and when you're done calling the function, restore it back from the stack so that nothing actually changed. And so that's caller save registers. Callee save registers is then just the exact opposite of that. So the caller is allowed to assume that the callee will not make any changes to EBP, EBX, ESI, or EDI. So there's this guarantee that if I call a function, it will not smash my values in these 4 registers. Therefore, if the callee wants to use those registers, it's responsible for saving them and restoring them so that, it can use the registers, but it needs to save them right away at the beginning. Go ahead, use them, blah, 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 write whatever values they want to use, and then right at the end, they need to restore them, and then they return to the caller, and the callee, have not changed anything in these registers, basically. So these are kind of conventions by which functions, they basically just divide up the responsibility of who's in charge of saving what registers, right? So caller is in charge of a few of the registers, callee is in charge of the other ones, and thereby, the compiler can try to generate code which doesn't use any of the callee save registers or something like that, so that it doesn't have to save them. And so the reason why I have to talk about this is because when you're looking at assembly code, you can potentially see some of these registers being saved for, at the very beginning, you'll see these being saved, and you'll have to say, okay, well, is this a callee save register? And if so, that's why this thing's saving it. And look, I can see it's saving it at the start and restoring it at the end. And this is just so that for your own purposes, you recognize what's the point of these pointless instructions, right? I see that it it saved it and then it restored it, so, it didn't do anything within this function to that register, right? There was a net no change, right? I came in, saved it, restored it, returned. There was no net change. And so what's the point of that? It's these conventions that they have so that there's only these limited number of registers, and it's really just, these 6 right here are your real general purpose ones, the EAX through EDX and ESI and EDI. Those are your kind of 6 general purpose ones, and therefore we've got this convention to make sure they don't get smashed by different functions. All right, so getting into their names and sizes a little bit. So, I've been talking about EAX, ECX, etc. thus far, and those are our 32-bit versions of the registers, so 0 through 31, 32 bits. And the point here is, originally, right, Intel was 16-bit, like I said. So in the beginning, there was AX, right? So there was the A for maybe accumulator, or B for like base pointer, or C for like counter. So there was AX, BX, CX, DX, and they were 16-bit versions of the registers. When they moved to 32-bit, they tacked on this E and it extended AX, right? So, so you need to know that actually there are these other forms, smaller forms of the registers that you can still actually access. So you may see assembly code trying to just access like the AH register. And then you're going to say, what's the AH register? We didn't talk about that. We know EAX. I never heard of AH before. And so this is just for your own purpose to know that there were these subdivisions of the large registers. You may see someone move something into a 32-bit register. They may move something into EAX, but then they may only pull out a byte by just grabbing something from AH or something like that, or AL. So, yes?
Excuse me, question. And can you refer to it that way, as AH or AL?
Yes, exactly. So you'll see in the instructions, if they're trying to grab some subportion of the register, they'll refer to it as AX or AL or AH, etc. So, and then you just have to keep in mind, like this up here, there is no notion for like the higher order 8 bits of EAX. There's no register named, anything up here. There's only for these lower order 16 and lower order, 16 as 2 different bytes. You can access each of those independently. So for these 4 registers, we've got all these forms where you can go down to like byte forms, etc. For the next set of registers, the SP to ESP. So originally you had stack pointer and you had base pointer, and then they became extended stack pointer, extended base pointer. And you can see none of these have shorter forms where you can access just a byte of them at a time. So just again, this is just for your own purposes to know if you ever see these short forms of them referenced, it's just some subset of this 32-bit register. And similarly, right, if we went to 64-bit, there's going to be this longer thing with R as the prefix, RAX, and then EAX is a subdivision, AX is a subdivision, AL and AH are subdivisions. So, all right, and then one special purpose register, which I'm going to talk about a bit, except I'm going to leave out a lot of details on this one, where I'm only going to ask you to remember a little bit about it. There's a register called E-flags. So this is a register that's 32 bits, so it's E extended. There used to be a 16-bit thing called just flags. And in this register, it's a series of single bits within it. And each of those bits, well, almost all of those bits have a specific name. So there can be something, for instance, called the 0 flag, and there'll be a specific bit position within E-flags which corresponds to the 0 flag. And what happens is, off to the side, whenever the CPU is doing some calculations, the results of calculations will be indicated in this flags register, this E-flags register. So let's say you're doing an add instruction and you added 1 to -1. The result would be 0, and this 0 flag would get set. And so I had a question in the last class, which was actually pretty good, which was saying, why don't we just check the register? If we want to see if the value is 0, why don't we just go and check if the register is 0 or something like that, right? The convenience from having this centralized flag register which sets a bunch of flags after every instruction is that, if you wanted to just check that, is some value 0, you don't necessarily know if that's going to be in the EAX register, EBX register, ECX, etc., right? So by having a central place where if the result is 0, you set the 0 flag in this register, having that central place, then you can just compare against a single flag. You can say, is 0 flag set? If so, I'm going to do one thing. If not, I'm going to do another thing. So the E-flags is used for most all of your, probably all, I can't think of any cases that this is not the case. It's used for all your conditional logic, basically. Yes?
Is that set after each?
After each instruction, yes. So every single instruction, behind the scenes, the hardware is updating these flags, toggling things on and off based on the past instruction. And the other thing I should say is that for certain, and in the manual it will say this instruction potentially modifies these flags in the E-flags register, right? So a subtract instruction will modify a certain number of flags, a multiply instruction will modify a certain number of flags, an XOR or an AND and things like that. They'll each have some set of flags which they can potentially modify based on the output result, right? And that's why it's potential modifications, because the result could be 0 or could not be 0, and therefore you can't just say the AND instruction always modifies the 0 flag, because if the result wasn't 0, it doesn't change anything in that 0 flag, or it doesn't set it. I think actually it may clear it, so maybe you could say it's deterministic in that sense. But anyways, yeah, so after every instruction, these flags in this register are updated, and therefore there'll be other instructions we'll learn about later which check these flags to say, if this flag is set, I'm going to do something. If it's not set, I'm going to do something else. That's where conditional logic comes from, basically. So the only two things I really want you to worry about in this class, just so you can have some notion, is the 0 flag, where if the result of the last instruction was 0, then we're going to set this flag to 1. Otherwise, if the result was anything else, it's 0. And then the sign flag, which is set equal to the most significant bit of the result. So going back to our numbers over here, Bill, back at the board. So we said before, like, F, 2, 4, 6, 8 equals -1, right? And then we said, that through 8, 0, 0, 0, 0, whatever that is. I don't know what that is off the top of my head. It's -2 billion or something like that. All right, so this is -1 and then -2 billion, and then you have 0 to +2 billion, right? Because you've got a 4 billion range with your 32 bits. All right, so we said these are all the, billion. And then we have 0 to 7F, F, 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 F equals +2 billion. Right, so these are our ranges for like positive and negative numbers for 32-bit things, right? And so the sign flag, so if you look at these and you take this most significant bit and you turn these, or most significant nibble, and you turn it into binary, right? 8 is 10000, F is 1111, 7 is 0111, and 0 is 0000. So what we can see, the commonality here is for negative numbers, they always start with 1 at their most significant bit. And for positive numbers, they always start with 0 as their most significant bit. So the sign flag has to do with, like, if the result is 854321, whatever, it'll be something that starts with 1, basically. If that's a negative value, it starts with 1. The sign flag will be set to 1. And, if it's something down here, the sign flag will be set to 0. And negativeness or positiveness is all in the eye of the code, actually, is what I should say. The hardware doesn't care about negative or positive. That's notions that we impose on some sequence of bits, right? The hardware only knows there's a sequence of bits. And that's why, for instance, if you have an add instruction or something like that, and I said after an add instruction, it updates a bunch of bits in this eFlags register. The add instruction, actually, the hardware does it as if this was adding signed numbers or unsigned numbers. It sets the flags accordingly in the eFlags. Basically, if this would have been an unsigned add, maybe the value would have been considered negative at the end. But if it was considered positive, then it would be set a different way. So you could have some border case here, right, where you add this -1. Right, well, I shouldn't do this because this is going to be overflow and it's not going to be real, but you can think of, right, these are two border cases where if I add these things together, right, they're not going to be positive anymore. These are positive numbers, right, but they're too big and they would potentially overflow into negative, but actually they overflow too far and they overflow back into positive. And so if I pick something more in like this middle range somewhere, whatever, if I took like 5 something plus 4 something, right, the addition of those would be 9 something, but 9 is going to be in this negative range, right? So were these two positives added together? Did that give me a negative, right? So the hardware doesn't care. The hardware just does, addition of bits the way bits are added. 1 and 1, 0, carry the 1. So behind the scenes, the hardware does instructions as if they were both dealing with positive values and negative values, sets the flags accordingly here, and the compiler is the one who's in charge of putting instructions which interpret those values as positive or negative, basically. And we'll kind of see that later as an example. You'll see where if you make a value as signed, you'll get certain sequence of assembly instructions, and you make it as unsigned, you get a different sequence, because hardware doesn't care, only the humans care. All right. Any questions about eFlags since I went into that a bit? Questions on the phone? All right. So 0 flag, set to 1 if the result is 0. Sign flag, set to whatever the most significant bit is. Alright, first instruction. Hooray! No-op instruction. Does nothing. It's pointless. It's not entirely pointless. It has its uses. Anyways, you're going to see this little star here. We have a new instruction. So no-op does nothing. Just there to potentially pad bytes or something like that. You put these instructions in, and maybe due to the Intel optimization guidelines, they'll say we want all functions to start on like a 16-byte boundary or something. So if the previous function didn't stop exactly at 16 bytes, you'll throw in a few no-ops until the next one starts on 16-byte boundary. And then they're used for making the canonical buffer overflows more reliable, but that'll be Corey's class. All right, so the late-breaking no-op news, which was late-breaking last year, but amaze your friends by citing this awesome x86 trivia. The no-op instruction, so this is quoted from the manual. The 1-byte no-op instruction is an alias mnemonic for the exchange EAX instruction. So we're not going over EAX in this class, but you can kind of guess what exchange EAX does. It takes whatever's in EAX and it exchanges with whatever's in EAX. So it does nothing, right? You're taking a value and just putting it back into the same register. So I had apparently never looked at the no-op instruction, right? You learn it and you say, okay, it does nothing. Okay, I can know that. But behind the scenes, it's actually this exchange instruction. So, for the people who know x86 and haven't taken this class, you can go up to them and be like, so, about that no-op instruction, I was wondering, how's that implemented behind the scenes? What does it actually do? And they won't know, because no one knows, because no one ever looks no-op up in the manual, because it does nothing, so why would you look it up? So, thanks to John Erickson for pointing this out to me. He had found this out through somewhere. I don't know where. It wasn't the manual, though. He had just seen it on some web page that he sent to me, and I was like, I don't believe you. I'm checking the manual. I don't believe some random web page. It's in the manual. Okay, so anyways, there you go. There's your first assembly instruction, no-op. All right, good. So now we're going to talk about the stack a bunch. The stack is a conceptual area of RAM, right? So by conceptual area, I mean, 1, stack is a certain type of data structure, and 2, it can be anywhere in RAM. It's just up to the operating system to decide where it wants to put it. And so when the operating system starts a program, it reserves some chunk of RAM, and it says, this is where I'm going to put the stack. And a stack as a data structure is a last in, first out, or first in, last out, however you want to call it. It's a last in, first out data structure where data is pushed onto the top of the stack, and then it's popped off the top of the stack before you can get to anything else. So, if I put the way the computer science classes talk about it, right, is you're at a buffet and you've got the stack of plates at the buffet, right? And if I put one plate on and I put another plate on, I got to take the second plate off before I can get to the first plate, right? So I can't jump under and pull them out because they're on a spring, and therefore they've got the guards on the sides. So you must take the thing off of the stack that you put onto it last. Now, by convention on x86, the stack grows towards lower memory addresses. So in this class, I'm going to be drawing, so there's a lot of, you need to have mental flexibility with this because you'll see this represented different ways by different people. But in this class, I'm going to be drawing low addresses at the bottom and high addresses at the top. That's like what you saw with our endianness diagram before, right? So I'm going to say 0 is at the bottom, FFFFF is at the top. And therefore, what you need to know about the stack is the stack grows towards low addresses. So that means they're going to be added going downwards, right? And the top of the stack is the thing which is lowest numerically. So it grows towards low addresses. The top of the stack is lowest numerical address, basically. So we'll get used to it once we start drawing a bunch of pictures of it. All right, and so we talked about register conventions thus far, and we said ESP always points at the top of the stack. And so specifically, it's pointing at the data which is being used on the top of the stack. So it's pointing at the lowest address, right? and therefore it's the least significant byte of potentially a little endian stored, 4-bit value or 2-bit value, or sorry, 4-byte or 2-byte, etc. But the point is ESP is always following the top of the stack, and therefore anything that's at a lower address than ESP, we're considering that undefined. That's like not really there as far as the stack's concerned. There may be real data there, but it's all, stuff that should never be accessed by a legitimate program, right? The compiler generates things so that it only ever reads data that's on, the top of the stack or below it, basically. All right. And so amongst its many purposes, the stack keeps track of which functions were called before the previous one. So there again, going back to that notion of stack frame, I can say, function main, for instance, is right here at the, so at higher addresses. And then when main calls, subroutine function 1, a new stack frame is started at lower addresses, right? Because the stack keeps growing towards low addresses. And so the stack keeps track of like which sequence of these frames has occurred, and it pops them off as you call a function. It gets a new stack frame, which is added lower numerically, but it's the top of the stack. And then when you return from a function, you take away that stack frame, and you go back up numerically, but lower on the stack. So again, we'll be showing plenty of pictures for this. But the stack is where you hold local variables or parameters passed to the next function which is being called, and the callee or caller save registers, stuff like that, is all stored on the stack. So really understanding this is very important, so ask questions as we go along if I confuse you with too much low, high, numerical, that sort of thing talk. All right, so our second instruction here is going to be push. You can push a word, 16-bit value, or a double word or a quad word onto the stack, right, according to the manual. But for our purposes in this class, we're only going to be talking about D words. You're only pushing 4 bytes onto the stack at once. And this value which you're pushing can either be an immediate, which is like a constant value that's hard-coded into the assembly instruction, or it can be a value in a register. So you can say push 4, and then we'll say that it's pushing a 32-bit value of 00004. Or you can say push EAX, and it'll say whatever's in EAX, the 32-bit register, stick that onto the stack. And then, question? Yeah?
Yeah. Can you push the instruction pointer value on the stack?
Not technically with a push instruction. So we'll see later how the call instruction implicitly pushes the instruction pointer, but you cannot pass. So when I say a register there, I guess I should have said any register except EIP. Or I guess then there's a separate form for E flags. You can push E flags, but it's separate instruction. It's not just push. It's like push F, I think. So anyways, so yeah, I should probably update that to say like any register EAX through whatever. All right, and so a side effect of the push instruction, right? So we're putting something onto the stack, and I said the stack pointer always points at the top of the stack. So if we push a new thing on, the stack pointer needs to move down by 4 bytes because we put a 4-byte thing onto the stack. We're going to decrement ESP by 4 so that it's still pointing at the top of the stack. So the last data on the stack, ESP should always be pointing at it. So this is sort of the side effect. So data will get added to this RAM wherever the stack pointer is, and then ESP will be subtracted by 4. So this is sort of the visualization of it. Like I said in this class, lower addresses are going to be at the bottom of the diagram, higher addresses up here, right? So you can see 80 plus 4, plus 4, plus 4, plus 4, minus 4, minus 4, minus 4. So we say this is what we're going to say the stack is before, and we're going to say we're going to try to execute this instruction push EAX. And so we're just going to say, okay, right now EAX has the value 3 in it, just picking some arbitrary starting value. And we're going to say right now ESP is the value 12FF8C. And that's 12FF8C. This is like a RAM address right now, right? So this is just your main memory. This is virtual memory. So ESP is pointing right here, which is the top of the stack. Right now, the thing that's on the top of the stack is the number 2. When I execute this push EAX instruction, ESP gets moved down by 4, and this value 3, which was in EAX, gets put onto the stack right here, right? So ESP still points at the top of the stack. This 3 got put into RAM, and ESP changed. So we said implicitly behind the scenes, this ESP register changed from here it was 8C to here it's 88, right? And so 8C minus 4 is 88. So C is 12, minus 4 is 8. All right. And then the corollary to push is pop. So if you want to take something off the stack, you just use pop. And pop can take whatever's on the top of the stack, whatever ESP is pointing to right now, take it off and put it into whatever register you specify, and then increment ESP by 4 in order to move it up and start pointing at a different point of the stack. So exact same thing backwards, right? If I then call pop EAX, let's say that EAX has FFFF in it by convention at the start, or by just arbitrariness at the start. So if ESP right now is pointing at 12FF88, right there, 12FF88, pop it. Now the thing is, like I said, everything numerically below ESP is considered undefined, but in reality there is data there. It's just you should never ever be accessing it. The compiler should never generate anything which will access it, and therefore we say that when I pop this 3 into the EAX register, this value right here becomes undefined, and there's nothing there as far as you're concerned, but actually the value is still there. You just took the value, copied it into the register, and moved the stack pointer. All right, any questions on push or pop quick? All right, now we're going to talk a little bit about calling conventions, and this is again one of those things where this matters to the people interested in reverse engineering and things like that. So calling conventions has to do with how you pass parameters to functions and how you get parameters back and things like that. So if I have function main and I want to call some subroutine, the question is, how do I pass the parameters to it? So let's say, well, we'll get into it more later. So just, there's only 2 calling conventions which we're really going to get into in this class. There's a bunch more which you can look up at Wikipedia and other places right here. But we're going to talk about CDECL, or C declaration, and standard calling conventions. So CDECL, C declaration, this is the most common calling convention. This is what you're going to see as the default typically for most C code, and some C++ code may default to this as well. And so the thing here is that function parameters, so whatever you're going to pass into this function, those function parameters are pushed onto the stack using push instructions from right to left. So if I've got some function, so I'm going to go this way, got some function, right? So say it's something like printf. You have printf, and then you have a string, and then you have some number of parameters afterwards which get interpolated into that format string, right? So printf, %d, and then my var, something like that. With CDECL convention, you push things from right to left. So you would push the address of my var, or the value in my var, onto the stack, and you'd push the address of the string %d, and then you would call the function. So you push them right to left, and then you call the function. In CDECL, the first thing that function does, so there has to be an agreement right between the person calling the function and the function itself. That's if you have mismatch in your function calling conventions, the called function will get messed up because it'll be expecting data in a certain way, like right to left, and you may be passing it in a different way. So both the caller and the callee must agree on this calling convention, basically. And so the called function here, the one which is accepting these parameters, the first thing that it does is it saves the old frame pointer, sorry. So it takes the old frame pointer, so that frame pointer was saying I'm pointing at main's frame, and then it says I'm going to save that address onto the stack, and then I'm going to set up my own new stack frame, and so I'm going to point EBP right here, and this will say everything below this is mine, and I saved a copy of the previous guys so that when I'm done I can go back and put that back to being the case. And then EAX or EAX EDX returns the result. Well, I think I have that backwards. I'm going to have to go check that. I feel like it should be EDX EAX, but But this is the convention I was talking about before in terms of when you want to return something back from the function which was being called, you're going to stick the value in EAX, or potentially if the value is 64 bits wide rather than 32, you would put it like half in EAX, half in EDX. I feel like the EDX should be in front, but I don't know. I better look that up. All right. And then this last bullet is really the one you want to put a star by. This is where CDECL and standard call differ from each other. In CDECL, the caller is responsible for cleaning up the stack for those parameters that it passed to the callee. And so what that means is, right at the beginning we said, function parameters are passed on the stack right to left, right? So you push, and then call. And so in standard CDECL, the caller, the one who pushed them onto the stack, is the one who's responsible for popping them off and getting rid of them, cleaning up the stack. And so down here in standard call, the only difference in all of this stuff at the top, that's all the same, and the difference is in standard call, the callee is responsible for cleaning up stack parameters. So that means, I know that, I'm a function and I know I got two parameters, and therefore I know I may as well go ahead and clean those two parameters off the stack before I return to the guy who called me. And so in standard call, they're responsible for cleaning that up before they return. And you'll see standard call being used by the Win32 API type stuff. So you'll be able to see based on the assembly whether something looks like it's using standard call or CDECL, because either you'll see something push parameters onto the stack, call instruction, and then moving the stack pointer to get rid of parameters immediately after the call instruction. If you see that, then you have to think, okay, well, that's CDECL. Caller pushed it on, caller cleans it up. If you see it pushing stuff onto the stack, it calls something and there's no cleanup, and then you go into that function that it called, and if there's a special return instruction which implicitly subtracts stuff from the stack, then that's standard call. But we haven't talked about the return instruction yet. So.
Just curious, but with CDECL then, does the function that got called have to push the stuff back on it after it popped it before it returns?
Did the function which gets called have to push it back on? So actually, the function which was called never actually took the stuff off the stack. So basically, it sits there on the stack in the previous function stack frame, and then this function will read that data out of the previous guy's stack frame, and it just leaves it there. And then when it returns, based on standard CDECL or standard call, it'll either return and stop at its own stack frame and just destroy its own stack frame, or it'll destroy its stack frame plus those parameters, whether it's CDECL or otherwise. But it doesn't always copy them off and have them be held in registers or something. They're sitting there on the stack the entire time, and it's just a question of who destroys them off the stack, basically. All right. Now we're going to talk about the call instruction, so we can see some of these calling conventions being used in practice. All right, fourth instruction so far. All right, so call's job is to transfer control to a different function, or change the EIP essentially, right? So behind the scenes, you can think that it's changing the EIP, but it's basically just saying, we know that programs are organized in, a series of functions where this has this functionality, this has that, and you want to call that from this. So call is the actual assembly instruction which implements this. It says, in the absence of a call, basically the CPU keeps incrementing EIP and it just keeps moving down, right? It's just going to go this instruction, then it's going to do the next instruction, then the next instruction, then the next instruction. So until we get to things like this, which alter where you want to go, the rest of the time it would just go, top to bottom. It would just execute an instruction, add however big that instruction was. So if the instruction was 1 byte, then it would add 1 byte to EIP, execute the next instruction. If that next instruction was 5 bytes, it'd add 5 to EIP, execute the next instruction. So the normal thing that the CPU is going to be doing is just executing instructions in sequence. Now when we get to things like the call instruction, when the call instruction is executed, the CPU is not just going to go to the next instruction in sequence, it's going to go wherever that call instruction tells it to go. So it's implicitly modifying the EIP. So there's some side effects to the call instruction though, right? So it doesn't just change the EIP and you don't just start executing somewhere else. you call a function and you want to have some way to return to the function which called it, right? So you typically, if you want to just go somewhere and never come back, then you use like a jump, or in C Notion you had like a goto, right? So goto says go there, and I don't worry about ever coming back, right? But we know in C, when I call a function, I expect it to do something, and then when it's done, it comes back to the next C line after it, right? And so in order to implement that sort of capability to go somewhere and then still come back to wherever you used to be, behind the scenes, call pushes the address of the next instruction onto the stack. So when you call something, you're going to change EIP to somewhere else, but you're also going to put the address of the next instruction onto the stack, so that later on when that something else is done, it can take that address off the stack using the return instruction and go back to wherever it came from. So the thing that's pushed onto the stack is sort of the little pointer that says, here's where I came from, please come back here later, right? When you're done, this is where you need to go back to. And the target of the call is where you're going to. So, yeah, so the return instruction, which we'll see next, uses that thing which is pushed onto the stack. And then it changes the EIP to the destination address, etc. So there's multiple ways that you can specify the target of the call instruction. So you can either give an absolute address or a relative address. And so an absolute address would say, like, I want to go to address 00401234, something like that. Right? So you just say, like, this is definitely the address I want to go to. And then the relative version says, I want to go to some address that's, hex 50 bytes past the end of the next instruction or something like that. So relative addresses are relative to the end of the next instruction, basically. Yep, so we'll go over that a little bit more next when we get to the actual. You'll see that more when we get to stepping through some actual assembly code. So you call instructions to go to a procedure, and you use the return instruction to come back. And so the return is actually implicitly using whatever that thing was that was on the stack pushed by the call instruction. So call puts it on the stack, and then return takes it off and says, okay, I'm going to pop it off the stack, and I'm going to go back to wherever that address was. And there's two forms of this, and these have to do with the cdecl kind of thing or standard call. So in the cdecl case, you basically just take whatever's on the top of the stack, return there, and that's it, right? And then the function who called you, they're responsible for cleaning up those stack parameters. In the standard call case, since the callee is responsible for cleaning up the stack parameters, the callee needs to also get rid of a certain number of elements off the stack, however many parameters it had. If it had 3 parameters, it knows that it needs to do 12 bytes that need to be removed from the stack. Get rid of those 3 parameters. So the second form of return is something you'll maybe see. So if you see the very end of a function, you see like a return 8 or a return 12 or a return hex 20, something like that. That implies to you that this is a standard call function because it's returning, so it's taking whatever's on the top of the stack and going back to that, putting the EIP there. But then it's returning, and then it's also getting rid of hex 20 bytes off of the stack or hex 8 bytes, etc. So the type of return instruction will kind of imply what type of calling convention was used in that function, as will the code that calls it, basically. All right, so we're almost to where we can talk about some pictures. All right, so next one is the move instruction. And this is used to move a variety of forms. So you can have something in one register and you want to put it in another register. So move one register to one register, some register to memory, or memory over to the register, right? An immediate to a register, or an immediate to memory. So again, immediate was like a constant which is hard-coded into the actual instruction stream. So it'll be move, and then they'll be in line with the rest of the bytes for that instruction. It'll be move and then hex 1, 2, 3, 4, something like that. So we don't talk about the actual bytes which define an instruction until the very end, but in the back of your mind you can have an idea that there's going to be some sequence of bytes which define an instruction, and immediate is a hard-coded constant. But the big thing you need to know about the move instruction is there's no memory to memory type of move. And so this is something which typically, at least this bit me a lot when I was first learning x86 assembly, and if I was trying to make a few hand-coded assembly instructions, I would want to like say, well, I know I have this value in this C variable stored in memory somewhere, and I know I have this value in that C variable, and I want to just like add, you know, that memory plus that memory and like add them and have them be destined for that first memory location. But you can't actually do moves or adds or subtracts or anything. Intel generally does not give you forms of instructions which will do memory-to-memory operations. So you typically have to take something out of memory, move it into a register, right? We have memory-to-register type of transfer, and then take a register in memory, and you can like move those or add those or things like that. So the main thing to remember is just you don't have any memory-to-memory form of move. And I'm going to make reference to it, and later on I'll say that there's a form that I'm going to call in this class an RM32 form, and that's how you specify a memory address. But that's just saying each of these places where I say you can do memory to register, that memory will be specified as an RM32 address form, and I'll talk about it later. All right, so now we start kind of showing a picture of some of our stack frames. So again, on my pictures, lower addresses are at the bottom, high addresses are at the top, and the stack grows towards low addresses, right? So as I keep adding stuff to the stack frame, I'm going to expect it to grow towards the bottom. And here we're just going to pretend that main is the first function called in any given program. It's not. There's some initialization code which happens before main, but we're just going to pretend the very first thing executed in any program is main. So we're going to say when the OS starts your program, it has main, and the first thing main does is it reserves space on the stack for its local variables. So it's going to do some subtract from the ESP in order to make a place for its local variables. And now, let's say that main wants to call some subroutine, which I don't think I've put on here yet. But okay, so main now is going to be the caller of a subroutine, right? So it's going to perform some caller saves on some registers if necessary, right? It won't always do this, but if necessary, if it's got values in these registers and it wants to make sure that the thing it's going to call doesn't smash them, it's going to perform caller saves on these registers. The next thing it's going to do is push onto the stack the arguments that it wants to pass to the callee. So that's what I said before. You go from right to left, pushing each of your parameters onto the stack. So that's going to be, you know, the rightmost parameter, the next most rightmost, and then the leftmost parameter, something like that, depending on how many parameters. Okay, so this is main's stack frame right before it actually calls the function, right? So it's not yet executed the call instruction. It's pushed the stuff onto the stack. It wants to execute the call instruction next to call some subroutine, but it hasn't yet. All right, so now when we execute the actual call instruction, the next thing that gets pushed onto the stack is that saved address of the next instruction after the call instruction. So that's put on there so that when the callee is done, it can just go look at this value and say, okay, well, that's where I need to go back to. Right? So this is sort of the little pointer that says, please come back to this location when you're done. Okay, and so now we executed the call instruction. This got pushed onto the stack. And so the first thing that subroutine does, and I need to go back and change the subs so that they don't look like subtract function or something, but this is just some generic subroutine. The first thing this subroutine is going to do is it's going to save the frame pointer for this previous thing. So right here, this is the entire main stack frame, and we said by convention EABP always points at the start of a stack frame. So I'm not showing it on this picture, we'll show it in later pictures, but you can think like EBP is going to be pointing at this very beginning of the stack frame. It's just going to be saying this is where my stack frame starts. So the first thing that sub is going to do is it's going to take that pointer, which points at the top right, top of the local variables there. It's going to save it onto the stack so that, again, when it's done and it's ready to destroy its own stack frame, it just takes that stack pointer, puts it back into EBP so that, again, it'll point at main's frame instead of its own. So it saves the previous guy's frame pointer, and then it takes its own frame pointer and it says, well, now I have my own frame and it's going to start right here, right? So everything from here and down is going to be subroutine stack frame.
Question.
Yep, question?
That's nice of it to do. But there's nothing enforcing some requirement that it needs to remember main state, right?
Right. So Amy's question was, there's, that's nice, and that's kind of you can do it by convention, but there's nothing enforcing that it needs to like save the frame pointer of the previous thing, and that's correct. Basically, if the compiler wants to be using this frame pointer convention, the compiler will generate instructions at the beginning of all these functions that say, I'm always like my first instructions, and we'll see this by the end. You'll get sick of these instructions. There's going to be 2 instructions at the beginning of all these functions which save the frame pointer and put the new frame pointer to the beginning of the new frame, basically. They don't have to do this, and you can set compiler options on your code which say, I don't even want to use frame pointers, and we're just going to have one huge stack thing, and like we'll have no notional difference between different frames, and that can mess with you as an analyst if you're trying to analyze things, to not have this nice division between stack frames. But typically the default case, people, unless they're explicitly don't want to use frame pointers, which if you ever see compiler options, they'll be like omit frame pointer option. If they omit that, then yeah, you won't have separate stack frames. But by default, and all the stuff we're going to see in this class, the compiler will always generate a thing that says save the previous guy's frame pointer and set up a new frame pointer starting at my code, or my frame. All right. And so the next thing subroutine is going to do is it's going to take any callee save registers that it wants to use, right? So if it needs to use some of those callee save registers, it will go ahead and save them. Actually, this is sort of backwards. I was looking at some, well, it's not backwards necessarily. Which order this happens in actually can be different. I guess I'm thinking of in the last class in GCC, they actually save the callee save registers after they make the local variables. So you can't guarantee that like the local variables will be first and the callee save will be next. But like somewhere in this stack frame, there's going to be some local variables and there's going to be callee save things. So actually, my note to myself is I need to go confirm again that Visual Studio saves things in that order. All right. So subroutine, it's going to save any callee save registers that it needs to, and it's going to create some space on the stack for local variables. So typically, functions right at the beginning, the compiler knows how many local variables you've declared in your function. So you may have, 2 ints or something like that. So the compiler knows you've got 2 ints, that's 8 bytes. Therefore, I'm just going to allocate 8 bytes all at the beginning. So typically, the compiler will allocate all your space for your it'll just create instructions to allocate all your space for your local variables on the stack at the start, and then the instructions it generate will, read into that local variable space based on where the compiler has put different local variables. So. All right, so now I'm going to have to kind of slide this stack frame up, and we're going to focus just on subroutines stack frame, and we'll kind of push mains frame up off the top. So now we're going to say, okay, well, that was nice. Subroutine had its local variables, had its callee save space. It can do its processing, etc. But when subroutine decides that it wants to call another subroutine, sub2, then it needs to go through, again, the exact same process that main did. It's going to take any caller save registers that it needs to save. It's going to push those on the stack to make sure that sub2 doesn't destroy its registers. And then it's going to pass any arguments to sub2, right to left, put them on the stack, and then it's going to call to it. So I think I didn't put the actual call to it, and I just said, this is kind of the last point, basically. So now, do I have another one? No, I don't. So basically at this point, it put those arguments onto the stack. It would call sub2. We could go through the exact same sequence, right? Sub2 would save the frame pointer, then sub2 would then, save its callee save, and then when sub2 is done, then it would destroy its callee save registers, destroy its frame pointer, return back up, and when subroutine is done, subroutine will basically clean up these arguments, clean up callee save registers, clean up its local variables, and so when any given function is done, it basically just destroys these things in sequence, and then it takes that saved frame pointer, I'm going to go back all the way to here, So let's say that sub, I think the reason I didn't put pictures is because I can just go backwards like that. So if I just execute the slides in reverse order, right, when sub is done calling, it's going to go ahead and, get rid of its, when it's done calling sub2, it gets rid of those parameters that it passed to sub2. And when sub is actually done executing, it's going to get rid of its local variables, get rid of its call save registers. Bam, it disappeared. And now it's going to take that saved frame pointer and it's going to replace EBP with this value so that it points back up again at the mains frame. And then it's going to take this called saved, this saved return address. It's going to take that, use a return instruction, and then that's going to pass control back to the function, the instruction after the call instruction, which was in main. So, and then main's back to this, and main would clean up, if main's doing standard call, main would clean up these arguments passed to callee. So, any questions on the stack frame creation? Like, just basically what these pictures are supposed to show you is this is kind of the maximum stuff that you'll ever see in one frame, in one stack's frame, but really at any given point, these things might not be here, like the caller, save registers, and arguments to a callee. Those may not be there because you're not calling anyone. You're probably going to have some local variables if you do anything of consequence, right? But you may not, actually. I guess in some of our sample code, we don't even have local variables. So you may not even see local variables. You may not see callee, save things. You may not even see a frame pointer. So it's possible to have a completely empty frame. But generally speaking, this is the maximum kind of stuff that you can actually expect to see in any given frame. So any questions about this thus far?
Will we see how information gets passed from one routine to another later?
Yep. So our first code example is going to be a super simple thing where a stack frame has nothing except a, where a stack frame has nothing except a saved frame pointer and the return address, for instance. Like, it won't even have any local variables or callee save things. And then once we get to example 2, then we're going to start seeing passing values to functions and stuff like that. So we'll go through much more concrete things than this coming up. But one other point I wanted to make here is that stack frames are actually sort of organized as a linked list. So this EBP, this saved frame pointer thing that I was talking about, I said the first thing sub does is it saves the frame pointer of the previous frame, right? And so this used to be pointing at the top of that frame, and now we're saving it and we're putting that pointer to the top of our current frame. And so it's essentially a backwards pointer to the top of the previous frame. And if I said the compiler's generating these instructions to always do that at the very beginning of every function, then as you go down, if sub saves EBP right at the top of its frame, and that points back at the top of the previous guy's frame, and if sub2 saves EBP at the very beginning and it points back at the previous, then what you essentially have is that the stack frames are basically a linked list way of organizing stuff where the most recent function, which is called the current function you're executing, is at the top of the stack, the numerically lower addresses, and the previous frames, whoever called you and whoever called the guy who called you, those are each, links back in this this chain of stack frames. So that's kind of the point of having this EBP frame pointer point at the top of your frames, and why you save it always at the beginning. It's to maintain this sort of linked list. And we'll see later when we're using the debugger that they'll typically, most debuggers are going to have a view where it'll say, show me the call stack. Where it's trying to say, like, show me which function I'm in and which function called me and which function called that. And basically all the debugger is doing is it's just taking those EBPs and it's reading it, it's going back. And how it figures out which function is which is because basically at the top, at the first value in the frame is that saved EBP, but the last value in the previous frame is that saved instruction pointer that the call instruction puts there, right? So when the debugger is going back, it can look at that chain and then it can say, okay, well, what's the value right above EBP? I know that's going to be something that was pushed by a call instruction, and therefore I'm going to look at that address and say which function is that address in, and therefore, that's an address that's within the bounds of main, and therefore that's the mains frame. And this is an address which is in the bounds of sub, and therefore that's a sub frame. So, All right. So I'm going to just give you, well, I'm just going to describe what we're going to do here with example 1, and then we're going to take our 10-minute break. And so with example 1, we have exceedingly simple C code. So we have main, and main calls a subroutine sub. And the only thing the subroutine does is it returns hex beef, right? So that's all it does. It doesn't even have any local variables or anything else. It just has this immediate value, hex beef, returns it, and then main doesn't even do anything with that return value. It just calls the function, doesn't even take the return value, and then just returns food anyways. So main just always will return food. Calling this subroutine is functionally, it does nothing, but what it does is it'll execute a call instruction. It will go into that thing. We will see a new stack frame being made, and then we'll see that stack frame being destroyed. So this will be the most basic level of stack frame creation, destruction, and function calling, etc. So these are all the instructions we've learned thus far, right? We said push this stuff onto the stack. Move, like this can move register to register in this case. Call, that's just saying I want to change my address to whatever is given. And then move, I can take an immediate, put it into a register. Pop, take something off the stack, and return, take whatever saved return address was put onto the stack by a call instruction, and pop that off and go there. So 10-minute break, back at 10:30, and we'll start going into this. We'll kind of go into it in excruciating detail where we'll look at every single instruction. All right.